Let us complete now example 8, with which we started at the end of the last lesson. We found out that the apex S of the cone that lies on the line L has to lie vertically above the midpoint of the diameter AB of the base face of the cone. We found the midpoint M of A and B simply by taking the average of the x-coordinates, the y-coordinates, and the z-coordinates respectively. Then, since the apex S lies on the line L, we know that its coordinates are just 5 plus t, 14 plus t, and minus 15 plus 3t. We want now the ms vector to be perpendicular to the AB vector, which means the scalar product is 0. Ms vector is s minus m coordinates always, so we get this vector here, scalar to AB vector being b coordinates minus a coordinates, and when we calculate that we get minus 12 plus 6t, we set that equal to 0, and we get t equals 2. Inserting t equals 2 here, we get s as 716 minus 12. The volume of a cone is 1/3 times the base face times height, so 1/3 times pi r squared times h. Since the radius of the cone is am and the height of the cone is ms, the volume formula becomes 1/3 times pi times am squared times ms. Since am is half of ab, this means it is half of this, so it's actually minus 2 to 1, which has the length 3, and we need it squared, so we get 3 squared, times the length of ms, which is this vector here with t equals 2 inserted. So we get square root of 7 squared plus 14 squared plus 14 squared, which is just 21. And we get that the volume is 63 pi units to the power of 3. The next two examples we're going to look at are about angle bisectors, and we'll start in example 9 with the angle bisector between two planes. Since the angle bisector is the set of all points that have the same distance from the two planes, in the end becomes again a question of distances, so try to solve it on your own. Stop the film here and then just continue when you feel like. I'll provide a solution here. We get the normal vector 2 minus 1, 2 to the plane P1, and N2 vector is obviously 3 minus 6, 2. We can choose a point A1 lying in P1. The simplest is to take 0, 1, 0, and a point in P2. I've decided for 1, 0, minus 1. So the distance of this point Q with just coordinates x, y, z from plane P1 can be calculated as A1Q vector scalar N1 vector divided by the length of the N1 vector, and don't forget here the modulus of this scalar product, and we get then for dqp1 this expression. The same thing applies to the distance of the point Q from plane 2. We just have to replace the normal vector by the normal vector of the plane 2, and obviously use A2, the point in the plane P2, to get this expression. And now what we have to do is just to set these two distances equal, since we're looking for all points that have the same distance from those planes. And we get this equation here. Note that there are still the modulus signs on both sides. This results in two equations. Sorry, there was a small mistake here. It's correct now. Well, we set the two equations now equal without the modulus sign, and we get the equation for the first angular bisector of these two planes, and setting the two sides equal but just minus the second side, we get the equation for the second plane. Now let us look at the second example, example 10 here, the angle bisector between two intersecting lines. And what we mean here by the angle bisector is the line that lies in the same plane as the two lines here. So something like this and like this. The idea how to find the angle bisector is to determine first the unit vectors of the direction vectors, and then we see that we get the direction vectors of the two angle bisectors, here this direction vector, as the sum u1 vector and u2 vector, or u1 vector minus u2 vector. So we have to perform now the corresponding calculations. u1 vector is hence this direction vector divided by its length, so divided by 3, and u2 vector, this direction vector, divided by its length, divided by 5. We could now calculate directly with these vectors, but to simplify our life, our additions, we reformulated the two vectors as 1/15 times a vector. That means I've expanded here by 5 and here by 3. And now the addition and subtraction becomes very simple. And I get u1 vector plus u2 vector is 1/15 times this vector, and u1 vector minus u2 vector is 1/15 times 5, 1 minus 22. And so I get finally these angle bisector lines, since the point of intersection S is given and lies on both lines.